All right, so here's the example that I want to prove. For every positive real number x, x plus 1 over x is greater than or equal to 2. Okay, so I'm going to prove this by contradiction. And to do that, it would help if I could get a symbolic statement equivalent to this one here. So I'm going to translate this from a sentence into a symbolic statement. I've written it in a way that it's already very close because I already have a for every, which is my for all. Right? This is going to be a quantified predicate when I translate it over. So for every, that's for all x, we're in the domain, let's assume we're in the domain of real numbers, and we're going to say for all x, if it's positive, right? If it's positive, x greater than 0, then this is the case. X plus 1 over x is greater than or equal to 2. So that's my P, and that's my Q. Let's do this again. P and Q. All right, P implies Q. And it's a for all statement. Now, if you want to negate that, this is, if I write down the negation of that, when you negate the for all, this, we're going to apply De Morgan's law here for quantifiers, and that's going to become there exists x, such that the negation of this implication is true. Okay, so now we can negate the implication. So that, as I showed in the previous video, negating P implies Q. Let me just make a note here to remind you. Negating P implies Q is equivalent to P and not Q. That's the way to negate an implication. So we're gonna say there exists x such that P, x is greater than 0, and not Q. Now, how do you say not Q? The negation of x plus 1 over x is greater than or equal to 2 would be x plus 1 over x is not greater than or equal to, but less than 2. Strictly less, right? That is the negation of Q. Negating greater than or equal to gives you strictly less. So having written it out symbolically, I have very carefully figured out what the negation is. I used De Morgan's laws for quantifiers, so now I've turned that for all into a there exists, and I used this thing to negate the implication and get P and not Q. So now my proof can begin with this. This is sort of like scratch work you might do on the side. And the proof will begin like this. Assume for some real number x, assume that x is greater than 0, and that x plus 1 over x is less than 2. Okay? For some, right? We're trying to prove this by contradiction, so instead of proving for every positive real this is true, we're going to say, assume that for some positive real number it's false, which is equivalent to this. X is positive, but, I mean, you might actually like to replace this with a but, because it really emphasizes the, negation aspect of it. It's like, assume you've got a real number that's positive, but it doesn't satisfy the thing. Instead, it satisfies the opposite of the thing you're trying to prove. X plus 1 over x is less than 2. All right, so now let's see what happens if that were to be the case. Well, then, equivalently, we could multiply both sides of this by x and write x squared plus 1 is less than 2x. I kind of skipped some steps, some algebra there, but just multiply both sides of this by x and distribute the x through on the left, and you get this. Now, this is valid. This is valid since x is a positive number. So you didn't have to worry about flipping that inequality symbol around like you do when you multiply both sides by a negative. Not an issue here because we're assuming it's positive. So I'm going to put that in parentheses. It's valid since x is positive. All right, so then I'm just going to move the 2x over to the other side. We've got x squared minus 2x plus 1 is less than 0. And I wrote this in standard form here. And then I can factor that. I'm just going to put an arrow here to say this implies the next thing, right? And you sometimes see an arrow, it literally means implies, because we're essentially working from one truth to the next truth. And we're saying we've got to here. Now, if that's true, then the next thing is going to be true. And the next thing is just an algebraic manipulation of this. We're going to factor that. X minus 1 squared is less than 0. Now, what's our goal here? We assumed the negation, right? And so our goal is to reduce this to the absurd. Our goal is to deduce some kind of contradiction. And that, my friends, is absurd. X minus 1 squared is less than 0. Well, that's impossible. So the next line of my proof is going to be, this is impossible, at least for a real number, x. Okay. Now, within that, there is a little bit of evidence, because certainly when you square like a complex number, you can get a negative, right? So if x were a complex number, this could be possible. But since x is a real number and x minus 1 is therefore also a real number, this is impossible. Okay, so just again, this is not impossible like all the time. It's just impossible in the domain we're working in. So that's our contradiction. Now, mathematicians like symbols. And sometimes you'll see this symbol, which is two arrows pointing at each other, like that. Or sometimes you'll just see that reduced to like an X with two lines through it. And that is just a symbol. It's abbreviation for contradiction. So you can write that symbol when you arrive at a contradiction in your proof as like a sort of a note, like a very like a marker, like this is a contradiction here. We've arrived. And so now I can kind of wrap the proof up and say, therefore, if x is a real number and it's positive, then x plus 1 over x must actually be greater than or equal to 2, like we wanted in the first place. And we did it.